Hello, and welcome to a discussion of virtualizing computer resources in digital special collections workflows. I'm Farrell from Duke's David M. Rubenstein Rare Book and Manuscript Library, and I'm here with my colleagues Shelly Black and Brian Dietz from the NC State University Special Collections Research Center. Next slide. To get started, here's a high-level overview of what we'll talk about. First, we're going to go into containerizing software packages for technical services work on digital archives, and then we'll transition into using virtual desktops to offer mediated remote access environments for digital archives. Next slide, please. Before really getting going, I wanted to spend just a moment briefly discussing virtualization in general. At its most basic, virtualization is the use of a host computer or server's resources to run other computing environments. And I'm using very general terms here because there are a lot of different ways one can accomplish this. The next slide, please. This example is using software to emulate legacy hardware. In the popular culture, at least in the video game subculture, this is probably the most commonly discussed type of virtualization. In the LIS and digital preservation context, you've probably heard or seen presentations from the emulation as a service folks or the software preservation network. Next slide, please. Here's another example, this time of a Linux virtual machine hosted on a computer cluster offered by campus IT for Duke faculty, staff, and students. Using an SSH protocol, the user logs into the command line interface and can do certain actions. At least in my institution, staff and our digital curation unit use these types of VMs as staging environments for our digital repositories. Next slide, please. Another common type of virtualization is desktop virtualization, where one uses a virtualization manager to run an entire GUI operating system and resources. Example here is using Windows Hyper-V Manager to run, at this point, a very outdated copy of the BitCurator environment. Next slide. And this final example is running a container-based a container based on a Linux image in Windows. The rest of today's talk will focus on these last two examples, so desktop virtualization and containerized environments. Next slide, please. Why virtualization? Generally, virtualization offers a couple of affordances. First, one is able to use software and processes in a separate operating system, such as Linux-only toolsets on a Windows host. And second, one has the ability to test processes in that separate environment. Because virtual machines are virtual, they can be more easily deleted and redeployed. And I'm glossing over a lot here, and colleagues in DevOps, systems, and software development could probably list off any number of other use cases for VMs. And we'll get into more specific motivations in each of our discussion sessions a bit later in the presentation. Next slide, please. And with that contextual information out of the way, we'll talk a bit more specifically about containerization for technical services, support, and virtual desktops for remote access.
Next slide, please. Thank you. Actions we commonly take in a born digital workflow include finding and removing duplicates from a larger file set, scanning for private and sensitive information and viruses, and removing or isolating the files containing it, characterizing files and gathering file system metadata, email reporting, and various means of file packaging. At NC State and Duke, for several years now, we've been doing the majority of this kind of work using command line applications. And a few years back, we started wondering about better ways to compile and manage these applications. And containers especially seemed like a promising option. Next slide, please. Before I go any farther, I want to provide a visual of what interacting with a container can look like. Lots of times as end users, we're likely interacting with containerized apps running on servers without even knowing it. In the case of what we're talking about today, we're running containers as desktop environments, which really kind of means running a virtual Linux computer with a terminal on your desktop. We're doing command line work in a terminal window, and this is really no different than what we've been doing at Duke and NC State. So what's different is how we're managing these tools. Next slide, please. So what's a container and what's its role in resource management? Like other forms of virtualization, containers allow one to package code and its dependencies in an isolated Linux environment so that they can be tested and deployed and trusted to work consistently across computers and computing platforms. The key difference between containers and, say, virtual desktop environments is that they share the host's OS kernel and do not abstract physical hardware or contain a copy of a full operating system, which is to say that they're intended to be lightweight. Docker and Podman are two popular platforms that support containerization, and there are several others. But just about all of the work that we've done to date has been done using Docker, and so that's the reference point for the rest of this section. Next slide, please. So in the context of this work, one builds an image and runs a container. An image is a base file system and the things necessary to run applications, so code, libraries, dependencies. And a container is like the running instance of an image. There's a general recommendation to have one application per container, so you're building only what you need. It reduces the risk of conflict between code and dependencies. And it should make the process of updating and rebuilding individual containers quicker and easier. A common example you'll see in Docker intros and tutorials is a web application that has one container for the application code, one for a data store, and a third for a Solr index. And the three can be run together like a single application. So far, what we've developed is a single image that includes ClamAV for virus scanning, Brunhilde for file format characterization, bulk extractor for PII searching, and file system analysis tools such as sleuthkit and walk2dfxml. So in this scenario, we're defining the environment as the application. Part of the reasoning is that some of the tools have the same dependencies, and those would become redundancies if separated out. Next slide, please. Okay, so how do you make an image? You build an image with a Docker file, which is a text file that contains the instructions for building the image. There are a limited set of terms you use to tell Docker what to do, and you combine those terms with commands that might be familiar, especially to Linux users. Next slide, please. So this is an example of a pretty simple Docker file. These are instructions to build an image for the sleuthkit, which contains tools used for examining media, disk images, and file systems. The from line says to build on top of the latest version of the Alpine Linux image. This image could be saved locally or pulled from the Docker Hub, which is a repository for images. And then on the run line, there are two commands separated by a double ampersand. First, we run apk update to update the Alpine package manager, which is apk, and then run apk add sleuthkit to install it into the Alpine image. For this example, I chose TSK because it makes for a short Docker file and it will build quickly in the demo. TSK could be a standalone service, but like I mentioned earlier, TSK is part of our production image. Next slide, please. To build an image with this Docker file in a terminal, I change to the directory where that file is and then run docker build-t for tag, how we name and tag an image, TSK, the name I want to give the image, colon, NDSA underscore demo, which is the tag, and dot for the current directory. Next. And here we have a very short video to show the build process. So the first thing you'll see is the ls command to list the contents of the directory so you can see that there's a Docker file in the directory. Then I run the command from the previous screen. And then you get some output, which can be very helpful to review, especially if the build fails. And we'll run this one more time. Thank you, Shelly. Oh, I forgot to say. So that whole process took 10 seconds, and about 1 second of that was the image building. It was probably that quick because I had a copy of the base Alpine image cache, but even without that, the build process would have been very quick. So our production image takes less than 10 minutes to build, and most of that time is installing bulk extractor. Next slide, please. So what was our motivation to explore containerizing our tool set? We manage a lot of command line tools for this work. Most are Linuxy, some are Python. We've been mostly working on Mac and using Homebrew, the missing package manager for Mac. It's great, but some things happen outside of Homebrew, like configuration. And also managing Python is a whole sort of different thing. There's also an issue with Homebrew on a multi-user computer that has a fix, but would be nice to avoid. We are expanding our workstations from Mac only to cross-platform, and some of what we do isn't possible on Windows or would be done differently on Linux. We'd like a way to manage, replicate, and distribute our toolset across workstations and provide a consistent user experience. I'd like to avoid desktop virtualization and keep things relatively lightweight. I'd like to avoid dual booting, and there's always the possibility of sharing this approach across institutions. And containerization checks most of these boxes. And Farrell, who's up next, will also later share more about what's missing.
Thanks, Brian. Yeah, in addition to everything Brian said about lightweight replicability, my main motivation for this work is related to our complicated desktop support environment. Campus IT offers limited services on what they call specialized computing environments, like those that we use for digital archives work. As you can imagine, this is a blessing and a curse. On the one hand, we have wide latitude to run whatever systems are needed, as long as they follow reporting and monitoring requirements. But on the other hand, that means I'm largely responsible for maintaining those workstations that our technical services staff use to work with Born Digital materials. Like Brian was indicating, our three workstations feature different configurations, which is not only frustrating to manage, but also means that our process documentation for staff varied slightly depending on the workstation in use. This led to end user confusion. Finally, as we've scaled up in our Born Digital program, we've shifted from using the GUI tools, like Brian was discussing, to a reliance on the command line and scripting. It's not to say the tools in BitCurator aren't good. It's great as a teaching reference. We just found that we were essentially wasting computing power by hosting two operating systems that had word processing software, PDF viewers, etc. Next slide, please. So with our related and overlapping motivations documented, how did this project get started? Began with the folks at NC State. As Brian mentioned, they had previously been managing Mac OS processing environments using Homebrew. Brian and Shelly began experimenting with building containers in 2020 and 2021. By the end of 2021, they had a working, although bloated, proof of concept based on Kali Linux. I joined as a collaborator in early 2022, and as a prototype, we built a single container on a Ubuntu Linux image, adding or editing applications and configurations as needed. And in 2023, both of our institutions moved into production with our containerized environments. Next slide, please. Across our two institutions, we've implemented production instances of images and containers for both AMD and ARM chip architectures, running Docker for Windows and Mac and Ubuntu Linux hosts. Further, NC State has experimented with Podman on the Red Hat Enterprise Linux host. Doing so has achieved the aims that we described earlier, ability to deploy environments across multiple host platforms with very little variation. But note that I said little variation and not no variation. So while I'm able to use the same Docker file on both my Windows and Linux hosts, the user has to issue slightly different commands to run the container depending on what their host environment is. Next slide, please. That note leads into some considerations that are potentially negative or at least not wholly positive. First, despite our best efforts, container implementations do differ across host platforms. That said, there is still less variation between Docker on Windows and Docker on Mac than, say, the entire Windows UI and the Mac OS UI. Second, this approach is a fairly large departure from the wider user base of the BitCurator environment. Since we're using many of the same component tools, we can still talk workflow and outputs with our peers, but the process for reaching those outputs has changed. I should say that we're still, all three of us, very active in the BitCurator community. Third, we still rely on IT support in some areas. All three of us are self-taught in administering containers and sometimes need help from experts. NC State University has relied on IT support for NFS volume sharing within containers, for instance. And finally, not every task in the curation lifecycle can be performed in the container itself. But again, there is less overlap between the activities that can happen in the host versus the container. For instance, viewing the contents of most files is happening in the host environment. None of these are deal breakers, at least to our perspective, and gives us plenty of food for thought for future work, while also having achieved our base level goals with this work. And with that, we'll transition to the second topic, covering virtual desktops for mediated remote access.
Hi, everybody. This is Shelly talking about the virtual reading room at NC State. This is a service that we offer remote researchers so that they can use Born Digital materials that we cannot put openly online due to copyright, privacy, or other donor-imposed restrictions. Before we began offering the service, if researchers wanted to use these types of materials, they had to make an appointment and come to our reading room. And there they'd use a laptop to view the materials. Wi-Fi and peripheral device ports are disabled on this laptop so that materials cannot be copied. We started working on the virtual reading room in 2021 while most of us were still working remotely. While most people have returned to in-person activities, researchers may still be unable to travel to the physical reading room. So there was and remains a need for remote access. At NC State, the infrastructure for what would become the virtual reading room turned out to be a campus service called the Virtual Computing Lab. This is an on-demand desktop virtualization service. What's being virtualized is located on a remote server in a data center on campus. And hypervisor software allows the server to run a virtual machine or the guest, and that shares its resources with the host's physical hardware, like memory and processing. Desktop virtualization allows the end user to use an operating system and applications running in the virtual machine, all through a graphical interface on their own computer. The virtual computing lab is usually used by classes and researchers to remotely access custom software and hardware environments. In the past, people had to visit an on-site lab if they didn't have software for their research or class. But by using the service, they can remotely log into servers running software for CAD modeling, DNA sequencing, statistics, and other applications. The software as a service is often available at universities adjacent to high-performance computing. It's also available as a cloud computing service from big tech companies like Google and Amazon. To see if the virtual computing lab would be a viable solution for the virtual reading room, Brian and I met with their systems engineers who quickly helped us realize how feasible this was. We got started by making an unending Ubuntu Linux server reservation for special collections. And then they also helped us figure out what settings needed to be changed. It was important to make the virtual reading room a secure environment that wasn't networked for users. So this included using the command line to configure Linux firewall rules, disabling the SSH client for users, and also disabling drive and clipboard redirection between the server and the user. All that to say, users cannot copy, download, or email materials to themselves. And then I installed open source software for viewing documents, images, videos, and other file formats researchers would most likely request. At this point, the settings and software were saved as an image, which is like a snapshot of the computer environment, and it's something we can reboot from. When public services staff assists a researcher and they determine that the researcher needs to use the virtual reading room, we'll send the researcher instructions on how to create an account. And similar to the physical reading room, the researcher requests materials and agrees to a terms of use. And then we send them instructions on how to authenticate and connect. The researcher would use software that's pre-installed on Windows, like Remote Desktop Connection. And on Macs, this is something they can download for free. And now I will play a demo of what it looks like for researchers to use this service. So here they're connecting to the remote server and then logging in using credentials they have through our university, or if they made an account, if they're members of the public. And this is a desktop interface. And they'll find the materials they requested in a directory with their initials or name. They can also copy materials they want reproductions of into a duplications request folder, which you just saw. And in this demo, I have different types of file formats that are being opened in open source software. LibreOffice is an equivalent to Microsoft Office, for example. And even though a researcher may have not had experience with logging into a remote computer, using the virtual reading room should feel familiar in that it's like opening files on our physical reading room laptop or their own computer. So here we can stream videos, MP3 files. So I'm hoping this gives you an idea of what it's like for the user or researcher to use this service. So in its first year of operation, the virtual reading room has benefited both NC State and external researchers. Unlike the physical reading room, multiple long-distance researchers can use the virtual reading room simultaneously and at their convenience. Another benefit is that the virtual reading room is relatively easy to set up by running a bash script I wrote that applies the different configurations. One should be able to reproduce it, given that their institution has a virtualization service or that they're able to pay for a commercial one. Desktop virtualization also offers flexibility. A virtual reading room could be deployed using a digital asset management system, a DAMS, or read-only cloud storage. However, a DAMS requires web development work, and those approaches are limited by the types of file formats rendered in a web browser. File formats used through desktop virtualization, on the other hand, are only limited to the software available. Virtual desktops also offer the potential for providing access to not just common file formats like you saw in the demo, but legacy files and software as well. For example, I've installed DOSBox and Basilisk 2 for emulating DOS and classic Mac games, which you can see on this slide. All researchers have succeeded in accessing and viewing their desired materials, with one exception, where the researcher couldn't connect, maybe due to a network firewall. Feedback has been overall positive, but there's always room for improvement. In terms of user experience, during testing, I found that video streaming quality has been inconsistent between ARM and Intel chip Macs, as well as different video containers or possibly encodings. So I'd like to do more testing there and also test using assistive technology with these virtual desktops. Additionally, I'd like to continue testing emulation with actual legacy file formats or software from our collections. Then finally, while I've briefly tested a trial version of Amazon Web Services virtual computing platform, I hope to return to that one or try Google Cloud and test running my configuration script there. So now you've heard about two uses of virtualization for digital archives. We're here because we're interested in distributing our configuration files and collaborating with others. So thank you everyone for taking the time to listen to our presentation today. And please don't hesitate to reach out to us by email, and we'd be very eager to share our scripts through from GitHub with you. Thank you.